Hello. I'm going to do a couple more examples of defining curves by vector functions. This will be a very short video. I wanted to do this at the end of the last one. So here are a couple of examples of curves of the form y equals f of x or x equals g of y, where x or y goes over a bounded closed interval. So first, let's take the curve y equals cosine x. X goes from 0 to pi, going from left to right. Now, sometimes in this class with the curve, we care about the direction. Sometimes we don't. And here, if we do care, this will go from left to right. And that's what the curve looks like. And I drew direction arrows there. I'll start with parametric equations. Since y is a function of x and x is free, I'll let x equal t and y is cosine t. And t goes, since x goes from 0 to pi, t goes from 0 to pi. Once you have the parametric equations, it's a piece of cake to write the vector function. You just take the two, the x function and the y function, and put them in a vector. Like that. So r of t equals t cosine t, and t goes from 0 to pi. And remember, for every value of t, r of t is the position vector of a point on the curve. And here are a couple examples. So that's r of 0 right there. That's r of pi. R of pi is pi 1. So in that example, y is a function of x. The next one, x is a function of y. So x equals t squared. X equals y squared. Y goes from -1 to 2, going upward. So I sketched the curve there, and it would be a mistake to solve this for y and get y equals square root of x, because y is not a function of x. The curve fails the vertical line test. That would be a big mistake. That's better. Yeah. All right, so x is a function of y, and y is the free variable. So let y equal t. And since x equals y squared, x equals t squared, those are the parametric equations. Since y goes from -1 to 2, t goes from -1 to 2. Once you have parametric equations, it's easy to write the vector function. You just take the x and y functions and put them in a vector. And since as t increases, y increases, so the direction is going up. And I'll draw a couple vectors there. R of 2 is 4, 2. That's what R2 looks like. I'll just draw one example. Now, why would you want to do this? In each example, I took a perfectly simple curve and I wrote it using a vector function, and it seems to make it more complicated. The reason for that is, suppose I knew how to do something for curves defined by vector functions, such as find their arc length or integrate a function along such a curve. And I had to do something like that for one of these curves. There are two ways I could do it. One way would be to memorize a special formula for curves like this, which might never be useful in this class. The better way is to take a few seconds to convert it to a vector function and then do it the same way as for every other vector function. So that's why you would want to do this. And I can't really show you a good example now because but trust me, this will be useful later. So that's about it. I told you this would be a short video. Next one will be longer. Oh, good. So next video, we will finally do some calculus with derivatives of vector valued functions.